Okay, so today we're going to look at hypergeometric distribution of probability, which is a very, very, very fancy name. But basically what it is a distribution of probability, again, the same as we did for our binomial distribution. But the difference is that we're looking for a number of successes and fails. But instead, so we have repeated trials. So to start with repeated trials, okay, we're looking for successes and fails. Okay, and most importantly, the key difference here, of course, because it sounds almost exactly the same as the binomial distribution, is dependent events. So instead of independent events where the probability stays the same each time, these are dependent events where the probability changes each time. So this would be what we would use if we were dealing out cards from a deck. Okay, and I don't know, we look at our hand of cards and a success is getting a 7. Well, what's the probability of getting 3 out of those 5 being 7s? Well, again, probability of a 7 changes each time that you either get a 7 or don't get a 7. And so as a result, we have to have a way to accommodate for that. And this accommodates for that, okay? If you were to put the cards back in the deck and sort of play some sort of card drawing game, then it would be an independent event, and we would use the binomial distribution. So same thing, repeated trials, success and fail, but here, dependent. That's the key. Okay, and that's what it is. So it's repeated trials, but instead of for the repeated trials, I'm looking for, I'm still looking for success and fail, but it's going to be probabilities that change. Now, there's an important designation. If you look at the last or the tail end of the independent events-based binomial distribution video, I talk about an example with a deck of cards where the cards are put back into the deck. That keeps the probability the same. That's independent, and therefore that's the binomial distribution. And then I also talked a bit about the whole idea of sampling. Okay, sampling is basically dependent events, but it does depend on how big your population is. If your population is the size of our classroom, or even the size of our school, although that's getting pretty big. If it's the size of our classroom, then the probability always changes when you sample something from a group. But if the group is 30 students, the probability number actually is, when you narrow it down to 2 decimal places or 4 decimal places, is a noticeable difference. But if you took it from the population of Mississauga, okay, which is on the order of, I don't know, hundreds of thousands to millions. I don't even know what it is now. But anyway, it's a huge amount. Then, of course, the number of males and females, for example, if a success was a male and a failure was a female, the number of males and females in the population, it doesn't change the probability, even though it literally does. The difference is what we call negligible, and as a result, doesn't change. So this is an example of sampling from smaller groups. Okay, and so that's a key feature. So if I'm, for example, has a success is getting a red Smartie, and I pour 3 Smarties out of a box, okay, and then I want to know the probability that all 3 are red. If they all 3 come out red, that's 3 successes. You would say to yourself, well, I only have, say, if it's a small Halloween box, like 14 Smarties in the box or something, and in a big box, it's probably like 30 or 40, I don't know. Okay, so the whole idea is those would be noticeable differences, and as a result, you wouldn't use this. This is for dependent events. You would use the binomial distribution. That's for repeated trials of independent events. But if I was taking 3 Smarties from the bin at Bulk Barn, where there's, I don't know, hundreds of thousands of Smarties, then the difference would be negligible in the number or frequency of reds. So the probability of reds wouldn't change, and as a result, we would have a situation where we could use an independent event. Okay, so that's something else to keep in mind when we're looking at these as well. Okay, so again, I go over the whole idea in the note of a success and a fail. Okay, it's the same thing. A success is the probability that you wish to know the probability, or the thing you wish to know the probability of. So what's the probability of, 3 out of 5 red Smarties? Okay, and a failure is not red. Okay, so a success is a success, a failure is not a success. Okay, now here, because it's based on combinations, we're going to be talking, and there's combinations in the last formula as well, but the combinations are for a different reason. But because this is based on combinations, we're going to be using pools like we did before. So we have a big universal set, then we have small subgroups. What we're gonna do is we're gonna break it into subgroups of successes and failures. Okay, so keep your eye on that as we go through it. Now, if you look at the formula, it looks crazy. Okay, let's stay away from that, and I'll explain to you how it works. The same way I explained the binomial distribution formula. So again, for hypergeometric distribution of probability, we still have two outcomes, success and fail. Okay, the trials are dependent. That's key. And of course, we have repeated trials that are seen as success and fail. Okay, so that's a key characteristic, but it's kind of assumed for these two distributions, whether it's a hypergeometric or binomial, that they're repeated trials, but that's okay. Okay, now, here's the key. If you look at this formula and try and diagnose it all, it gets really, really complicated really, really quickly. Okay? So, what we have to think of is, basically, this represents our successes. Okay, and what we're going to be doing is we're going to choose our successes from a success pool. Okay, so let's say, I don't know, there's it's a bin, no, not the bin. It's like a Smarties box. Let's say there's 10 red Smarties, okay, out of a total of 40. Okay, and I take 5 out, okay, and I have, I don't know, 3 of those 5 are red. And I want to know, well, what's the probability of that happening? Okay, what's the probability? Well, a success is going to be red. So that means I have 10 reds to choose from, okay, and I end up getting 3 of them. Okay, so it would be a 10, choose 5. That's how I can get my successes from a pool of successes. Okay, this focuses on failures. Okay, and in the note it's outlined a little bit better, you know, it's failures from a pool of failures as well. Now, the pool of successes and failures all add up to your totals. So this is the total elements in the pool, the big pool, the universal set, and this is the total trials that you do. So if it was a box of Smarties, it would be 40, choose 5. Okay, I had 40 Smarties and I sampled 5 of them. Okay, this would be a 10, choose 3, because I had 10 red Smarties and I'm choosing 3 from them. And then this would be what's left over. And that's really what this is and this is, what's left over. Well, what's left over from 10 taken from 40 is 30, because there's 30 non-reds. I don't know what colors they are. And then I took out 3, okay, but it's 3 taken from the 5, so there would be 2 here. And that's where the subtraction comes from. I'll show you with an example so it's not as weird. The other thing that messes a lot of people up is if you don't memorize what these letters are and you sort of do it practically the way that I showed you, there's a bit of a pitfall. But this is the probability of success to start with, at the start. And this R is my number of trials. Okay, so that's something that maybe you're going to have to take a bit of time to get used to. But I have a good example here of taking things from pools. Okay, so I'm going to take things from pools. We've already done this. We already did this in our assignment for our probability unit, as well as for if we have a test for the test. We're not going to have a test for the stay-at-home stuff, but maybe this is for a later demo. That's fine. But either way, what we're going to be doing again is choosing from a group. Sampling is a great idea, whether it's sampling people from a group or whether it's sampling Smarties, whatever. So let's look at the next example, or the first example. So there are 4 grade 9s, 5 grade 10s, and 6 grade 11s who are volunteering. Okay, from these volunteers, Mr. Hanley needs 6 of them to be football managers. Okay, so 6. The 6, okay, first of all, it's repeated trials. Yes. Okay, because I'm getting 6 of them, taking them out, plucking one at a time, boop, 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 boop. Whether they give in resumes or whether I just picked them from a lineup, whatever it may be. I'm choosing 6 of them to be football managers. Okay, so we have repeated trials. All right. Can they be viewed as successes and fails? Well, it depends. We haven't really asked any questions yet. That's just a circumstance. But we know we're doing repeated trials. And also notice it's a small group of 4, 5, and 6. So my total is going to be 4, 5, and 6 is 15. And I'm choosing 6. So I've got repeated trials. I've also pretty much set up the denominator of my formula, but I'm not going to get to that yet. Let's look at our first example. What's the probability of Mr. Henley having exactly 2 grade 9s? Okay, so we have repeated trials, a small group that I'm taking them from, so it's going to be dependent events. But here, I have probability of 2 grade 9s. So what's the probability of 2 grade 9s helping out? Okay, so what's a success and a fail? So a success is going to be 9s. And a fail is going to be not 10s, not 11s, not 9s. Okay, so in this case, I usually tend to draw a little diagram, but you don't have to, but it's useful if you do. Okay, so you've got your successes, and then you've got your fails. And generically, it's always going to be success and always going to be fail. Okay, now the successes are going to be the 9s. I have 4 grade 9s, so there's 4 grade 9s for my success pool. For my failure pool, it's going to be the not grade 9s. Okay, and there's going to be 11 of those, because remember, I had a total of 15, so 4 plus 11 is 15. Okay, in total. And then I'm going to make a subgroup. I'm going to take from this pool and take from this pool and create my group. Okay, so I'm looking for the probability of 2 grade 9s, exactly 2. So probability of x is equal to 2 because I have 2 successes, 2 9s. Okay, first thing I'm going to do is I'm going to set up my chooses. I'm going to go choose, choose, choose. Okay, my first choose, I'm choosing my successes. So it's going to be 4, choose 2. 4 to choose from, and there's 2 that I choose, or 2 successes that I have. Okay, I know that we usually start with NF, so I'm going to go back to that in a second. Okay, this of course is going to be multiplied, or you can use brackets if you want to. Then what I have to do is I have to make the rest of my group. There's 6 football managers, so that means that the rest of them are going to have to be from my 11 failures, or from the other 2 groups. So these would be 9, and these would be 9 primed. Okay, and I have to choose 4 more of those to have my group of 6. And who do I choose from? I choose from a group of 11 people, or I choose from failures. So that's me choosing my successes. That's me choosing my failures. I can only choose successes from a success pool and failures from a failure pool. Finally, of course, I have my totals. What am I really doing? Well, I have a total of 15, and I'm choosing 4 plus 2, 6. These numbers and these numbers always add up. 4 plus 11 gives you 15, and 2 plus 4 gives you 16, because this is my pool, pool, and this is choices, 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 or samples, samples, samples. Okay, then I just do my simple bit of arithmetic, and at least the math here is not too bad. I'm going to cheat and use my notes. 6 times 3, I didn't know this off the top of my head. And again, if you don't want to reduce that or write it in lowest terms, again, what we tend to do is the probability of 2 9s as managers is, and I got a nice beautiful closing statement, 0.3956 approximately, because we did have to round that. Okay, so there you go. That's how we use that formula. It's not as crazy as it looks. It's not as intimidating. Okay, we're going to do expected value a couple more times after this, so we'll get to that. But let's do a couple more examples of just the formula when we're doing that, because we're going to start doing ranges of ones too. Okay, so hopefully that's okay. We'll move on. All right, now another example, same group. So if you remember, we had 4 grade 9s, 5 grade 10s, and 6 grade 11s. We're choosing 6. Okay, so hopefully you remember that idea. If not, have that page handy in front of you. Here, what's the probability of Mr. Henley having at most 2 grade 9s helping out? Now, first of all, the word at most 2. What does that mean? Okay, so I'll draw my pools. Again, I already have it from the previous page, but that's okay. We're talking about 9s again. We could change this to grade 10s, in which case a success would be a grade 10. But either way, there's my 9s, and these are my not 9s. So that's not, I shouldn't go 9s because it looks like a compliment. Erase that. It won't erase, please. Okay, there we go. All right, so the 9s and then 9 primed. Okay, remember we had 4 grade 9s and we had 11 who are not grade 9s. Okay, the rest of my grouping. And remember, I'm still choosing a group of 6. So I know that somehow from both pools I'm going to have to get 6 individuals. Okay, so what am I looking for? Well, it's a probability of at most grade 9s. At most means I can have 2 grade 9s, or I could have less, but I can't have more than that. So it's a probability of x being less than or equal to 2, which means we have the probability of 2 plus the probability of 1. So it's, I can either have 2 or 1, or I could conceivably have none. And I got lots of grade 11s and grade 10s to choose from. Okay, so it's certainly possible. And so we're going to do 3 different probabilities. It's good practice for this formula. Okay, we've already done this one, but that's okay. Let's do it from scratch. Okay, so for this one, it's going to be choose my successes. So 4, pool, choose, and I'm going to choose 2 of them. Okay. And then I'm going to go, well, if I chose 2 of these guys, I'll just do it light, 2. Well, I guess I can draw the line nicely. But in this case, 2, which means this is going to have to be 4. And so I'll choose my failures, 11, choose 4. And remember, we got O over totals. Okay, so we've got 15 total. Yep. Choose, and then I'm choosing 6, and I'm choosing 6 plus 2 and 4 gives me 6, 11 and 4 gives me 15. So that all adds up, which is nice as well. Then we go ahead and do it for 1. Okay, now we do it for 1. We're going to be choosing 1 from the success pool. So I go 4, choose 1. And then I go 11, choose 5. Why is it 11, choose 5? Again, I've got 11 failures to choose from, and I'm going to have 5 because 1 plus 5 is 6. And again, that's got a total 15, choose 6, 4, and 11, 1 and 5. Okay, and that works out. For choosing 0, you may seem kind of silly, but we do still have to do a probability for that. In this case, it's a 4, choose 0. Successes, failures, all 6 have to come from the failures pool, and I'm left with 15, choose 6. The nice thing is the denominators are common. Okay, so keep the denominators common. That's going to be 5,005 for all of those 3. If I'm remembering from the previous page. Oops, and I can also cheat off my notes. I have them to my left. Tricky, tricky. Okay. And that's going to be 1. Oops, that's for 0. So that's 1 times 462, pretty big number. This is also, oops, that's 4 times 462 because 11 choose 5 and 11 choose 6. They're both the same. Remember Pascal's triangle? You know this. Anyway, so 462 for both of those. And then if you remember from here, we had 6 and 330. So if we were to add all those up again, multiply the numerators, then add them all up. Order of operations important. And we end up with, I've kind of run out of space here, I've written too big, 0.8571 is the correct answer. Okay, and of course that relates to the probability of at most 2 grade 9s are in my group of 6 for my managers. Okay, so that's the idea. Not too crazy, okay, not too insane. All right, the formula looks a little daunting to begin with. The name, very, very intimidating, hypergeometric. Wow, it's a good thing to impress your friends with at parties if you want to. But anyway, let's move on to another example. Okay, in a bowl there's 12, oh, that's a Smarties example, 12 orange Smarties, 10 yellow Smarties, 6 red Smarties, and 6 green Smarties. I'm going to total those up first. So that's 22 plus 12 is 34 in total. Okay, I'm grabbing 5. Okay, I know I'm doing repeated trials. I'm not just getting 1 Smartie. Okay, and it's from a small group, so I know it's a dependent event, and the probability is going to change each time, depending on whether I get a red or not a red, or a green or not a green. Okay, so let's move on. I'm grabbing 5 Smarties, so repeated trials, dependent events. Okay, what's the probability of grabbing 3 green Smarties? Okay, so that's a success-fail measure there. Okay, my success is going to be green. And for my green group, how many were on my greens? I have 6 greens, which means I got a whole bunch who are not greens. Okay, 6 from 34 is 28. Or you can add up the 12 and the 10 and the 6 and get 28. And I'm going to be choosing a small subgroup, a little bitty handful of 5. Okay, I want to know the probability of having 3 successes. Okay, in this case, 3 greens. All right, so first I'm going to choose from my green pool. There's only 6 of them, and I'm going to get 3 of them. Then I'm going to, I'm not going to use the times multiplication sign there. Then I'm going to have to show 3 in that way, 3 in that way. And then I'm going to have 2 of my not greens. So 28, choose 2. Again, 2 and 3 total to 5. 6 and 28 total to 36. And of course that's, sorry, 34. And that's 34, choose 5. Those should work out that way, plus make sure it makes sense. I've got a 34. From a total of 34, I'm choosing 5, so yes, that makes sense as well. Okay, you don't want to use the way that you check things to cripple you into thinking that you have an answer right when you don't. Okay, so make sure, so verify it in 2 respects. Again, I'm just cheating, finding the numbers. I have my calculator here, but I'm being too lazy. I'm just looking at my answers to the left. So you crunch out those numbers, and that's the easy part. And so then you're going to have, therefore, the prob of 3 greens in a handful of 5 Smarties is 0.2355. Okay, whether it's Smarties, oops, I think of my answer key I put M&Ms, but that's okay. I guess it doesn't make a difference. M&Ms or Smarties. Okay, now we do an expected value. Again, one of the real powers and benefits of this sort of process of distributions. Now remember, the expectation for repeated trials is an expected number of successes. So when we say expected value, you think it's a value. Okay, and you're like, oh, these are colors of Smarties. We can't have values. No, it's a number of successes. We've quantified a success as being green. Okay, so this is how many green Smarties would you expect? So the expected value. I'm going to do that calculation again for the previous one. It seems a little off. 20 times 3, 2, 7, 6. Well, maybe it's okay. I don't know. Yep, it's good. 28, choose 3. Where's my choose again? Choose 3. Okay, that's right. My bad. All right, sorry. I just had a bit of a brain fart there. All right, so when we do this formula, remember, it's going to be R times A over N. But in reality, really what you're looking for, okay, is the probability of success the first time. That's what I've circled there. So what's the probability of success the first time? 6 green out of a total of 34. So 6 out of 34. Multiplied by my number of trials. Okay, in this case, which is 3. Oh, sorry, 5. We're getting 5 Smarties. Okay, so that ends up being 30 out of 34. And therefore, you would expect 30 to 34, 0.88 number of successes. Okay, 0.88 greens in 5 Smarties or in 5 trials. Okay, even if you pour them all out at once, remember each trial is an independent process. Okay, but the probability changes as each one pops out of the box. Okay, so that being the case, there you go. Okay. Now here, I just pivot a bit and I change what my success is, okay? Because here I say, what's the probability of grabbing at least 3 orange Smarties? Remember, I'm still doing a handful of 5. There's a couple of words in here that are difficult. So first we've got an O primed. So that's orange and not orange. That's my successes, okay? How many oranges do I have? I've got 12, which means how many do I have the rest? 22, totaling to 34. And I'm still grabbing 5. Now here, it's at least 3. So not only is it 3, it's a probability that X is going to be greater than or equal to 3, which means it could be 3, or it could be 4, or it could be 5. It can't be any more than 5 because we're only grabbing 5 Smarties. I guess we could keep on going if we were grabbing 10, which would be a bit of a difficult scenario, or we go 1 minus the ones we don't want. Anyway, so let's figure these out, okay? So if I'm grabbing 3, first I'm going to grab some oranges, then I'm going to grab some not oranges. So I'm going to go 12 for 12 oranges, choose 3, multiplied by who's left over, 22, choose 2, and that's going to give me my 5, or my 34. Choose 5. Probability of 4 is going to be 12. Choose 4 successes. Again, choosing successes from my success pool and choosing failures, who's left over from my failure pool. There's only 1 left over because 4 plus 1 is 5. Or from 34 Smarties, I'm choosing 5. Finally, and I know this seems kind of ridiculous, but we choose successes from the success pool, and you're like, well, we have no one else to choose. Yeah, but it's a good idea to see it. Also to see the patterns in the distribution. We know this is going to turn out to 1, and it's going to be inconsequential in the calculation. Okay? But either way, there it is. Now, I'm not going to crunch out all the numbers. I didn't even crunch them all out in your solution set. I just turned them into final probabilities. But I get a probability for this, plus a probability for this, plus a probability for this, and it's going to total to and we total because we add all three of them up. The probability of at least 3 oranges is, and again, you can look, if you don't like this video, you can look at the nice solution set that I have for you. Don't worry about that. 0.2638, so approximately equal to 0.2638, and that's the probability of having that particular circumstances. Of course, logically, to go along with that, okay, 3 Smarties out of 5, should we expect that amount? So we have an expected value in this case for, we could put an O in there for orange, the expected number of oranges that we would have. And in that case, again, remember the probability of an orange the very first time around is 12 out of 34, and there are 5 trials, which leaves me to 60 out of 34. Therefore, we would expect, what is it, 1.76 orange Smarties. Okay, and that's the scenario. Again, sorry about my writing. The numbers are at least clear. Have a look at the nice, beautiful problem set, solution set that I have to these notes, and you can see them a little bit better. Just to simplify the whole idea of expected value, okay, if we grabbed 17 Smarties, okay, how many of those would be, okay, from the same package that we had? Orange. So the expected number of orange is going to be, again, the probability of orange is still 12 out of 34 multiplied by my 17. The expected number of yellow, well, we got to go all the way back. There's 10 yellow. So it's going to be the probability of success the first time, 10 out of 34. And we're going to multiply that by 17. For the expected value for red, again, we got to take the probability of red, so that's going to be 6 red out of a total of 34 times 17, and the expected value for green, and that's going to be, again, green, if you remember, was 6. There was 6 of them out of 34 multiplied by 17. If you figure out what these actual values are, there's 6 there, there's 3 there, there's 5 there. They don't always work out the whole numbers. I just set this up nicely because 17 Smarties is half of the box. I don't know if you saw how tricky I was there. Okay, but notice it's 6 and 3 and 5 and 3. That's 8, 9, 10, 11. Plus 6 is 17, so it does add up to 17 for all of the outcomes there. But more importantly, look, I have 12 orange Smarties. If I take half the box, I would expect 6. I have 10 yellows. If I take half the box, I would expect 5. If I have 6 reds, if I take half the box, I would expect 3. And if I have 6 green, I take half the box, I would expect 3 as well. So go on ahead and give these a go. This is homework for your new textbook. So if you're using the old textbook, if you're online, you're going to be using the old textbook. Then the questions that are assigned are actually going to be in your lesson folder for the hypergeometric distribution. If you want to use a new textbook, you can try these, and you can ask me those ones. Just let me know if it's a new textbook question or old textbook question. So hopefully that's okay. Talk to you later.